What is simple harmonic motion? If the restoring force of a vibrating or oscillating system is proportional to the displacement of a body from its mean position and it is also directed opposite to the direction of displacement, then such motion is called simple harmonic motion. As you can see in this figure, if we displace the mass m from its equilibrium position, then there is always a restoring force which wanna restore the mass to its equilibrium position. But this restoring force is always opposite to the displacement. Mathematically, the restoring force can be written as F equals minus Sx, where S is nothing but constant of proportionality and it is called spring constant. Also, it is called stiffness. Here, the negative sign shows that the restoring force is always acting against the direction of increasing displacement. And please also note that S value depends on the nature of the spring. It is large for a hard spring and small for a soft spring. Here is mass spring example. When the spring is stretched by pulling the mass m from its mean position to the right side, then after some time t, the mass is at displacement x. And due to elasticity, the mass tends to back toward the mean position. The force that restoring mass to its mean position is called restoring force, and that can be written as F equals minus Sx, as we have already discussed this formula on the previous slide. So, because this restoring force is always opposite to the displacement, that is the reason we have negative sign here. Now from the Newton's second law of motion, F equals ma. Hence we can write minus Sx equals mx double dot, where x double dot equals second derivative of x with respect to time. This equation further can be written as x double dot plus omega square x equals 0, where omega square equals s over m. And omega is nothing but angular frequency of oscillation. Equation 2 is equation of motion of the simple harmonic oscillator. Please note that if the total change in the length is small compared to the original length, then in that case the magnitude of the restoring force is linearly proportional to the displacement. Now to solve this second order differential equation, multiply both sides by x dot and then integrate with respect to time. As you can see, I have done this step over here, where by doing the integration with respect to time, from this part I get 1 over 2 x dot square plus half omega square x square equals constant, and this constant supposed to be a. Now further solving this equation, we get x dot equals omega into 2a over omega square minus x square under the root, which further can be simplified by doing the integration, and that can further be written in terms of sine inverse, and that is sine inverse x over 2a over omega square under root equals omega t plus c. We have initial conditions here, that is t equals 0, we have x equal x naught, and by using the initial condition we get c equals to sine inverse into x naught over 2a over omega square under the root. And this further can be written now, sine inverse x over 2a over omega square under root equals omega t plus sine inverse into x naught over 2a over omega square under root. Further, by simplifying, we can say sine inverse x over this term equals omega t plus phi. And this whole term we call now phi. And this is how we can write now x equals xm sine of omega t plus phi, where xm is nothing but equals to this term. So x equals xm sine of omega t plus phi, where xm equals 2a over omega square under root and phi equals sine inverse of this term. And please note phi should be vary between 0 up to 2 pi. And this xm is nothing but the maximum value of the displacement, which is nothing but amplitude of the motion. And phi is called the phase angle or phase constant. and equals to sine inverse x naught over 2a or omega square under root, and where the limit of the phi is between 0 up to 2 pi.